Hey everyone, this is a video on how to calculate the seismic design force on a non-structural component for ASCE 716. So this is a type of question you might face on the California Seismic PE exam. It actually would fall under category number 4 from the test plan that's put out by the board. The seismic principles test plan, and that would be seismic forces, non-building structures, components, and equipment. So again, we're looking at chapter 13 of ASCE 710 for the seismic force, specifically the horizontal seismic design force on a non-structural component. So what do we got here? We got a frame, elevation of a frame. Frame is spaced at 20 foot. It's about 55 foot in height there. You got an electrical cable tray. That's 10 foot off of the third level. Okay, that's a point of attachment there. You're given that the tray weighs 20 pounds per linear foot. The design spectral response acceleration is 1.25. The risk category is 1. And the tray powers an ice cream room at a new startup. That is not an insignificant note. Okay. So the way you start out this calculation is head over to chapter 13. You'll find equation 13.3-1. Equation 13.3-1 looks something like this. So it's F sub P is equal to 0.4. That's A sub P. A sub P is the component amplification factor. You got your spectral response design acceleration, SDS. You got your seismic weight for the component W sub P, and then all that's going to be divided by R sub P over I sub P, where R sub P is the response modification factor for the component, and then I sub P is the importance factor for the component, and you're multiplying that by 1 plus 2 times Z over H, where Z is equal to the height or the elevation at which this component gets attached, and H is equal to the height of the structure it gets attached to. So what do you know? What do you got here? You got Z and H, you got WP, you got SDS, you got AP, you got IP, you got RP. What do you know here? You got SDS, which we've given you. You've got W sub P, which is a seismic weight, which you can actually figure out because you could go W sub P is equal to 20 pounds per linear foot, okay? And what's the spacing? Well, the frame is spaced at 20 foot, so you're gonna go 20 pounds per linear foot times 20 foot. You got 0.4 kips. That's your seismic weight, okay? Now what's Z? Well, you've got Z. Z is a point at which the component gets attached, which you can see here is right about 50 feet. Right there, that's 50 feet. Okay, so Z is equal to 50 foot. Now what's the height of the structure? Height of the structure is 55 foot. Okay, what do you not know? So we've taken care of these guys here. We've taken care of that guy. What do you not know? You don't know the amplification factor, you don't know the response modification factor, and you don't know the importance factor. So how do you find the importance factor? Well, as I said, this detail that I put in here is not insignificant. So the importance factor is obviously determined about how critical this thing is to the function of the structure, and obviously it's going to impact in the end the overall load that this thing is going to be designed to. So if you go to section 13.1.3, it actually gives you details for the component importance factor. How much is that? What affects that? Is it 1.5? Is it 1.25? Is it 1.0? So based on the stipulations given, if the component is required for the function for fire life safety purposes of the structure, or it conveys some type of toxic material, it's attached to a risk category 4 structure, and it's needed for continued operation, and then if it contains hazardous substances, you're going to apply 1.5 importance factor. Otherwise, you end up applying a 1.0 importance factor. And there are a number of exemptions given in section 13.1.4, which you should read, based off of the type of component and the seismic design criteria. Now, what's been given here is that this is powers in ice cream room at a new startup for risk category 1 structure. So we're going to go ahead and say the importance factor here is 1.0. Okay? Next, we've taken care of that. The amplification factor and the response modification factor. So for those, you're either going to reference tables 3.5-1 or 3.6-1, and that's going to depend on the type of component you have. So 3.5-1 has architectural components, 3.6-1 has primarily MEP components. So if you reference 3.6-1, you'll see a line item in there for electrical conduit and cable trays, and that's a category we fall under. So reference that. Your amplification factor is equal to 2.5, and your response modification factor is equal to 6.0. Okay? Now, we can go ahead and calculate F sub P, because we have actually, just to highlight those off, okay, we've got everything. So we've got 2.5, we got 1.25, got 0.4 kips. Okay. Now what does that come out to? So that's actually going to come out to 0.23 kips. Okay, but wait, we are not done yet. So we've calculated the horizontal seismic design force on the component. However, just like you see in chapter 12 when you're calculating the seismic coefficient, there is a minimum and there is a maximum that you need to consider. Okay, so if you reference equation 13.3-2, which I note there, you'll see that that gives you the maximum force that we are designed to, and that's given by F sub P is equal to 1.6 times SDS times I sub P times W sub P, and that ends up coming out to 0.8 kips when you multiply all of that together. And then there's a minimum. So let's say this is the maximum, this is the minimum. Okay? And you're seeing the bonus question there. You're not supposed to see that one yet. So F sub P is equal to 0.3. And again, this is the minimum. SDS I sub P and W sub P. And that comes out to 0.15 kips. So where do we fall? We fall right in between the two. So that means our answer is going to be F sub P is equal to 0.23 kips. All right. Bonus question time. What vertical force should the component be designed for? So if you reference section 13.3.1.2, much like in chapter 12, where you're given a vertical seismic design force that you typically add on to the dead load in your load combinations, you've got the same thing here, where section 13.3.1.2 lets you know that you need to include a 0.2 SDS, a plus or minus W sub P, or the seismic weight. So what vertical force should the component be designed for? So consider your worst case load combination. That force is going to be P sub U is equal to 1.2 plus 0.2 SDS. times your dead load. In this case, it's really just W sub P, your seismic weight. And then P sub U ends up coming out to 0.58 kips. Okay? And that is how you calculate the seismic load, horizontal and vertical now, on a non-structural component. Thanks so much.